Welcome back to the twisted side of science. It's time to learn about the basic laws which define everything what you perceive as reality. In my last movie, I've tried to explain how the fractal dimension of scale determines the rate at which time flows in physical space, and that time on subatomic scales flows so fast that existence of matter becomes just a probability in a determined timeline. Of course, 95% of so-called professional scientists will tell you that everything what I've tried to explain is nothing more than a new age pseudoscientific bullcrap which is completely against mainstream theories invented 100 years ago and still used as the base of standard model. But the sad truth is that in 95% of those cases, their education and general interest in knowledge ends up with the diploma and official title. I spoke with many educated physicists, but only a couple of them seemed to be interested in a scientific discussion, and I really thank those couple for their time. I'm always ready to hear a professional opinion and speak a bit about science. It's said that there is so few professionalists who are not afraid to lurk in the unknown territories of non-mainstream science and look beyond the official academic doctrine. But I have to warn the 95% who follow blindly those with authority and successful scientific career. If you think that mainstream science has all the answers and that my blasphemous claims are a complete pseudoscientific nonsense, you might be surprised. Before you call someone a stupid ignorant and laugh out his crazy theories, be sure to check out your own knowledge. Do you know anything about recent trends in science and theories which were developed after the first half of 20th century? We are living in the time of global communication. All you need is a bit of will to get a wider perspective on a discussed subject. How many of you heard about fractal space-time geometry and scale relativity? This theory is made specifically to make a smooth connection between quantum and classical mechanics in a single model of physical reality. And yet, my claims are being treated as some new age metaphysical fairy tales. Problem is that I know what is the main cause for the general lack of public interest and why those with authority in theoretical physics seem to pretend that such theories don't exist. It's because anyone who knows something about theoretical physics is probably able to see where it all goes. Scientists don't want to unify the science because they are afraid of scientific and obvious truths. It's not that easy to admit being wrong. Luckily, there is also a brighter side of science. In my last movie, I presented the research of a couple professional scientists who are not afraid to challenge the mainstream with innovative theories. Since I'm trying to be fair, I sent them emails to let them know that I've used their work in a movie. I also asked them if they would like to look at my own ideas regarding the fractal geometry of time-space. I received only one answer from Sergei Fedosin, who is the creator of a theory called infinite hierarchical nesting of matter, which described the fractal structure of universe. I'm proud to tell you that Mr. Fedosin was kind enough to place the link to my movie on his Wikiversity site. During last couple of weeks I've read some of his publication and I have to admit that he has a great knowledge of many fields in theoretical physics. I won't lie that I was able to understand everything in those publications, but I understood enough to see how innovative are some of his theories and ideas. For me, he's a physicist who rightfully earned my respect. It's sad that among the scientific society his name remains almost totally unknown, just like most of his theories. I hope that one day world of science will appreciate the work of those few who are not afraid to challenge the generally accepted assumptions and search for new ways. Anyway, just like before, I will let him know that I used his name in this movie. Maybe he will be able to find some time to give a short professional opinion about my non-professional model of the speed of light in relative motion, which I want to present you in this movie. In the end of my movie, called Unified Relativity, Simultaneity of Events and Proper Order of Timeline, I asked if someone who has proper education in physics can describe a simple scenario using special relativity. Two observers, incoming at each other at 25% of c, and a third stationary observer located between them where paths of motion intersect each other in one space dimension. Here's the animation. First, the perspective of third stationary observer. point is to describe this scenario in a proper way using one of moving objects as a stationary frame of reference. Here is the same scenario observed from the perspective of red sphere. Of course, in this scenario, blue and red spheres are incoming at each other with the same speed, so velocities of objects are transformed symmetrically for both perspectives. From the perspective of blue and red spheres, velocities of incoming objects are exactly the same. From the perspective of yellow sphere, red and blue spheres are moving at 25% of c. If we use the Galilean model of relative motion, then for blue and red spheres, yellow sphere moves at 25% of c, and second object is incoming at 50% of c. This is how my scenario is represented on time-space diagram for the perspective of stationary yellow sphere. And a second time-space diagram for the perspective of red sphere in Galilean relativity. I've managed to find only one person who is currently studying relativity and had the will to describe my simple scenario using the laws of Einstein's special relativity. I would like to show you the results which he presented me. This is his time-space diagram for the perspective of blue sphere. Yellow sphere from animation is represented here by green color. It is moving at 25% of c. Velocity of red sphere is equal to 50% of c. Everything seems to be consistent with animation and my own diagram. But this is where problems begin. Using the laws of Einstein's special relativity instead of Galilean model, if we want to change the perspective to a different frame, we have to transform the time-space coordinates in a specific way which is known as Lorentz Transformation, LT. I've explained the basics of this subject in one of my previous movies. Here is the diagram for stationary yellow sphere after applying Lorentz transformation of coordinates. As you can see, according to diagram, all spheres intersect a single point in space dimension in the same point of timeline, as for the blue sphere. However, distances passed by moving objects are no longer consistent with the animation. And now the last diagram. This one represents motion of spheres from the perspective of red ball, which on the first diagram was moving at 50% of c in relation to stationary blue ball. Of course, time-space coordinates went again through Lorentz transformation. Values presented on this diagram are completely inconsistent with the animation. Not only distances passed by moving objects are different than for the blue ball, but also the moment at which paths of all spheres intersect takes place around half of a unit later than for other two spheres. Symmetry of motion, on which this scenario was based from the beginning, is completely gone after Lorentz transformation was used. According to mainstream science, Galilean model of relative motion can be used in all the cases where velocities of frames in relation to constant c are relatively low, like in our everyday life. When velocity of an object in relation to light is high, we have to use special relativity and operate on the time-space diagram using Lorentz transformation. Although I'm not a professional physicist and my opinion doesn't matter at all, I think that a proper model of relative motion should work just as fine for all relative velocities of moving objects. As a matter of fact, it doesn't matter if object moves at 0.05% of c or 95.5% of c. From its perspective, light is always moving at 100% of c. And this is why I would like to show you a simple simulation created in a 3D software which I made only to see if Galilean model of relative motion can be used at velocities which are high in relation to the speed of light and what results will we get. As always, my model is as simple as it can possibly be. Everything you need here to create a virtual model of time-space is the constant velocity of light. I like to deal with simple numbers when I want to define some basic laws of my model. This is why, in this virtual simulation of reality, light moves through 1 unit of space distance in 10 frames of animation. At the bottom of the screen is a frame counter. This is everything what you need to create a working model of constant c in relative motion. I will now use this simple model to represent visually scenario which I've discussed earlier. Two objects moving towards each other at 25% of c and a third stationary object placed in the location where paths of motion intersect in a single space dimension. As you can see on the diagram, blue and red spheres are passing 2 units of space in 8 units of time. We can say the distance of 2 light years is being passed by them in 8 years, or 1 light second is passed in 4 seconds, what means that both objects are moving at 25% of c. To make things simple, let's assume that red and blue spheres cross a single point in space dimension after 4 units of time, 40 frames. This means that in this time both spheres pass the distance of 1 space unit. And this is how this scenario looks like in my virtual environment. I hope that for now everything is clear for you. I've tried to make it as simple as it can be. Next step is to change the perspective to one of the moving spheres, let's say red one. First, let's look at the visualization. From the perspective of red sphere, yellow sphere is now incoming at 25% of c, and in 8 units of time it passes 2 units of space, while blue sphere moves at 50% of c, and in 80 frames it passes 4 units of space. To get a valid representation of this animation on the time-space diagram, I will have to use Galilean relativity model and transform the coordinate in a way which scientists called boosting. Everything seems to be consistent with animation. Yellow ball is passing 2 units and blue ball 4 units of space, while their paths of motion intersect each other after 4 time units. So, it seems that up until now, the Galilean model of relative motion is the one which allows me to describe my scenario in a valid way. Lorentz transformation of coordinates leads to a result which doesn't properly represent my simple animation. But now it's time for a more difficult task. Let's see if my simulation, which is based on classical Galilean relativity, will be able to handle the constant speed of light in all frames from the scenario. Let's see if from the perspective of red sphere, light is moving in all directions at constant c, 10 frames for each 1 unit of space. And something is not right here. After 10 frames, distance passed by light emitted from red sphere seems to be different than for the light emitted by stationary yellow sphere. Something is obviously wrong here. During 10 frames of animation, light is supposed to pass a full unit of space for all 3 observers in the scenario, but it doesn't. And this is exactly why, according to special relativity, in order to maintain constant value of c in all frames, we should use the Lorentz transformation of coordinates. However, as I explained earlier, this process completely destroys the simultaneity of events and proper order of timeline. So maybe there is another way. You see, entire problem comes from the fact that while measuring the distance which light is passing, we are using the same grid of space coordinates as for stationary yellow sphere. However, from the perspective of red and blue spheres, yellow ball is no longer stationary but moves at 25% of c, and the grid of space coordinates moves together with it. If we want to measure distance in the stationary frame of red sphere, we have to use grid of space coordinates which is stationary for the observer. Can this be done? Sure. And the solution is pretty simple. All we have to do is to attach the coordinate grid to a moving sphere. If the grid is moving together with observer, from his perspective it is stationary. Here you can see the movement of two coordinate grids in respect to each other. And now let's get rid of one grid and look once more at the simulation from the perspective of stationary red sphere with stationary space coordinate grid. And now let's see once more if constant speed of light is maintained in stationary frame of red sphere. Now everything seems to be okay. Light passes 1 unit of space in 10 frames of animation. Of course, if we try to describe the perspective of any other sphere using space coordinates which are stationary for red ball, we will end once again with incorrect results. Dimensional space moves always with observer and appears to him as stationary. Only the respective frame of stationary observer is valid. Time and space exist for each observer individually. Everything what is observed by a stationary observer in his stationary frame can be treated as definitive. If I am able to determine the order or timeline in a process which takes place in my own frame, this timeline will be definitive. And if the same process will take place in your stationary frame, it will happen for you in the same order as for stationary me. But if you try to observe from your perspective a process which is taking place in my frame, you might observe it in a different way than I did. Our perception of frames which are moving in relation to us is distorted due to the apparent nature of velocity in relative motion. It means that we need to transfer time-space coordinates each time when we want to describe the perspective of an observer who is moving in relation to your own stationary frame. In shortcut, it doesn't matter how your frame is perceived by anyone except you or those who are moving with the same speed and in the same direction as you are. What matters is how you observe your own stationary frame. Not so long ago, I made a movie about simultaneity of events in relative motion. We consider that events which are observed as simultaneous in a stationary frame might appear to happen in order for a moving observer. However, simultaneity is maintained for both in their own respective stationary frames. Although it might sound like some kind of philosophy, definitive and relative perception is a crucial aspect of relativity. I will now try to use my simple simulation to explain one of the greatest mysteries in theory of constant velocity c in relative motion of objects. Let's assume that blue and red spheres emit a single pulse of light in the first frame of timeline. Point is to learn what is the time at which light emitted by one of the spheres arrives to a moving frame. Keep in mind that distances and velocities of spheres are different for yellow stationary sphere and for those which are moving in this frame at 25% of c. From the perspective of red sphere, in the first frame of animation, yellow sphere is located 1 space unit away, while blue sphere is placed 2 space units away from observer. If all the spheres would be stationary in relation to each other, light emitted from the red sphere would get to yellow one in 1 unit of time, 10 frames, and to the blue one in 2 time units, 20 frames. However, in this scenario, all spheres are incoming at each other. Light emitted from the red one moves at 100% of c towards other objects which are moving closer to emitted light. Distance between source and receiver is getting shorter with each passing frame. In the first frame of animation, yellow sphere is located 1 space unit away from the red sphere. After 10 frames of animation, light emitted by the red sphere passes 1 unit of distance in space, but at this time yellow sphere is already much closer to the source of light. In the beginning of animation, there was exactly 2 units of space between blue and red spheres, but blue sphere is moving towards red one at a relative speed of 50% of c. After 20 frames of animation, light emitted by red sphere passes 2 space units. However, during this time, distance between both spheres was already reduced to 1 space unit. Now, let's look from the perspective of red sphere and see at which frame of animation emitted light seems to reach the incoming spheres. According to the simulation, from the perspective of red sphere, light emitted in the first frame of animation reaches the center of yellow sphere at 8th frame, or after 0.8 unit of time. And now, let's see at which frame light emitted by red sphere reaches the blue sphere from the perspective of light source. According to the simulation, from the perspective of red sphere, light, which is emitted in the first frame of animation, reaches blue sphere in 13th frame. And because in this particular scenario, blue and red spheres are moving towards each other with the same speed, 25% of c, such result is valid for both perspectives of light sources. For both red and blue spheres, light which they are emitting is reaching incoming objects at 8th and 13th frame of animation. It seems also that 8th frame of the animation is quite important for this scenario, as for all three spheres, at this moment of timeline, emitted light seems to reach the incoming object, yellow one for perspective of red and blue spheres, and all other objects from the perspective of yellow light source. As you probably noticed already, those numbers of frames in the animation appear to be a bit off, as until now I was working only with complete units of time and space. However, according to simulation, light reaches the moving spheres in 0.8 and 1.3 time units. This is why let's see if those results are still consistent with the time-space diagram. Let's start with the perspective of stationary yellow sphere. And guess what? Simulation seems to be totally consistent with this diagram. As you can see, from the perspective of yellow sphere, red and blue spheres cross the arrow of constant light speed right at 0.8 time unit and in 8th frame of animation. But just in case, let's look at time-space diagram for the perspective of stationary red sphere. It seems that just like in the simulation, yellow sphere is crossing the axis of constant c in 0.8 unit of time, what is equal to 8 frames of animation. And lastly, let's look at the 13th frame of animation. And once again, time-space diagram shows exactly the same story as the simulation. Blue sphere is crossing the axis of constant c at 1.3 unit of the timeline, what equals to 13 frames of animation. It couldn't be any better for my simulation. I would like to make a small bet. Anyone who wishes to defend Einstein's theory of special relativity and has the proper knowledge of this subject, this is your chance to show me that officially approved model of relativity is capable to describe this simple scenario in a better or more accurate way than the one represented here. I wonder if there is anyone on this planet who will accept this challenge. Good luck. I hope that up until now everything is clear for you, as things will get now slightly more complicated. You see, for now I was describing this scenario from the perspective of light sources. However, let's now try to describe the scenario from the perspective of a sphere which is a sensor or receiver of light, emitted by a source in motion. And this is where we are getting to the bottom of the whole trickery of constant c in relative motion. Couple minutes ago I was talking about definitive perception of observer's own frame and a distorted perception of relative frames. How do you think? Which perspective can be treated in this simulation as a definitive one? Perspective of a light source or perspective of a light receiver? If according to a stationary light source, photon emitted in the first frame of animation seems to reach an incoming object in 13th frame, then in which frame light will reach a sphere which is being treated as a stationary receiver? Will we end up with the same result? And if not, which observation can be treated as proper one and which as distorted perception of relative frame? If you are able to guess the answer to this question, I can be proud of myself, as it means that I've managed to properly explain my model of relativity. But if you have absolutely no idea what results will we get and how to understand them, don't worry too much, as I will now try to explain the general principles of apparent and definitive perception in relative motion. Let's look at the scenario from the perspective of blue sphere, which is now treated as a stationary receiver of light pulse which is emitted in the beginning of animation by red sphere, which is moving towards stationary blue ball at 50% of c. I've made a small update of the simulation. Now the incoming red sphere is emitting a pulse of light every 10 frames of animation for the first 3 units of time. Those of you who saw some of my last movies, or those who know something about relativity, should be able to recognize the well-known pattern of Doppler's effect on frequency rate of a light source in relative motion. I will soon show you how Doppler's effect is involved in a process which is responsible for the whole confusion in the subject of relativity. First of all, let's see in which frame of animation light emitted by a source which is incoming at 50% of c gets to a stationary observer located 2 space units ahead. And now listen carefully, as here is the solution for all apparent problems with the constant c in the classical Galilean model of relative motion. First of all, remember about the symmetry of relative motion, which comes from the fact that for a sphere stationary frame, both spheres are moving in the same speed in opposite directions of space. Symmetry of velocity addition plays a key role for objectivity of observation. I believe that this is the cause of disagreement and apparent craziness of constant c in relative motion. My model uses a good old Galilean way of velocity addition, as it is probably the only solution which gives us valid result in this simple simulation. In the classical model of relative motion, for two objects moving in opposite directions, quarter of c plus quarter of c equals half of c. In special relativity, nothing is so simple and intuitive. In the first frame of timeline, there are two space units between blue and red spheres. Both objects can be treated as sources of light. Let's assume that both spheres emit a light pulse in the first frame of timeline. This leaves us with two distant and simultaneous events. According to Einstein, simultaneity of unrelated distant events is apparent. In Einstein's model, an observer who is moving in relation to those spheres would experience a non-simultaneous variant of relative and equivalent timelines. In my theory, there is only one definitive timeline which is valid for all observers in their stationary frames. In my model, each point of timeline is associated with a specific situation which happens just once in history. But there is one issue. Simulation predicts that light emitted in a stationary frame seems to get faster to an incoming object than light emitted by incoming object and observed in stationary frame. Light emitted by a stationary source reaches the incoming sphere in 13 frame, but light emitted by the incoming sphere needs 20 frames to get to the stationary observer. In both cases, distances between spheres are equal in the moment of light emission. Einstein's solution for such disagreement is acceptance that contradicting results are equally objective. In special relativity, there is no such thing as definitive simultaneity or proper order of events. There is no timeline which would be valid for all observers. I would love to see how someone tries to use special relativity to create a working model of this simple scenario. I will stick, however, to my model of light in relative motion, which requires a single timeline valid in all frames. And this is why I have now to decide which prediction is valid and which one isn't. In the end, only the valid result will be observed. Maybe one day someone will try to test my scenario in a laboratory. It should be possible with modern technology and hadron colliders. It would be a stupid thing to assume that we will observe all possible results in a single measurement, unless we are discussing quantum mechanics. Truth is that in case of this scenario, there can be only one result. Light will reach the incoming object in 1.3 or in 2 units of time. Only one outcome can be true. So let's try to learn which result is the right one. Couple minutes ago, I made an important statement. I've said that the only objective observation is the one observed in a frame which is stationary in relation to the observer. If we will apply this rule to this particular situation, we will be able to point out the fact that from the perspective of stationary sensor, light reaches the observer after 2 times units. And because this observation is made in a stationary frame, it has to be the correct one. Besides, we have to remember that in the moment of light emission, distance between the spheres was equal to 2 space units, and because speed of light has to be constant, pulse has to travel this distance in 2 units of time. Those both arguments are enough for me to point out the correct result. However, since we're dealing here with physics, it would be nice to support my claims with science. Entire problem is based on the fact that distance measured in a moving frame using stationary space coordinates grid is always different than the same distance measured by the moving observer. Of course, just like any else, this effect of relativity is also symmetrical, so an incoming object will be affected by distortion just like a stationary one when we switch the perspectives. In my scenario, this symmetry is especially important as both red and blue spheres are moving with the same speed and move through the same distance in the animation. So everything what is experienced by one of the spheres will be experienced by the second sphere as well. We can use this property of relativity to look for a solution for the problem, which is being discussed. Let's see how the Doppler's effect affects the space in a moving frame. The best way is to measure the distance between pulses of light emitted by the incoming sphere. Let's begin from the space in front of the incoming sphere. According to space coordinates of stationary red sphere, there are 5 impulses of light in front of the blue sphere, and they are distributed in 2 units of space. It seems as well that distance between each 2 pulses equals exactly half space unit. Since impulses are being emitted by spheres each 10 frames of animation, distance between each 2 pulses should be equal to 1 unit of space. And this is exactly what we see from the perspective of stationary observer. There is only one way to explain this phenomenon. It's because of the Doppler's effect, which is compressing the space in front of incoming light source. Let's now see what happens with the space behind the incoming blue sphere. Using the space coordinates of stationary red sphere, we can measure that behind the incoming sphere, 5 pulses of light are distributed in 6 units of space, and the distance between pulses equals to 1.5 space unit. Of course, just like before, it is also caused by the Doppler's effect, which works always in both directions of one space dimension and depends on the direction and velocity of relative motion. Space behind a moving light source is extended just like it is compressed in front. Here you can see how the Doppler's effect affects the space in front and behind of a light source which is incoming towards a stationary observer at half c. The smarter part of my audience should be able to notice something interesting. There seems to be no symmetry in the rate of compression and expansion of space in front and behind an incoming light source. According to the simulation, distance of 4 space units is being compressed to 2 units in front of blue sphere, what means that space gets 2 times shorter in front of a light source, which is incoming at 0.5 c. However, behind the same incoming light source, 4 units of space are extended only to 6 units, what means that distance gets 1.5 times longer. It's because the radius of circle gets 50% shorter on one side, while on the second side it gets 50% longer. Let's now use those values in the simulation. And this is a moment when I can prove once again that my concept of time being a wave function instead a linear dimension is very useful in discussing the rate of time flow in space. I will begin from the time space in front of incoming light source, where, as I said some minute ago, distance in space gets 2 times shorter. This is why I will now decrease the wavelength of light on the left side of blue sphere. Done. Now let's focus on the time space on the right side of blue sphere. As I said earlier, distance behind a light source which is incoming at half c seems to get 1.5 times greater. Let's apply this value to my simulation. Ready, but now there's a new problem. After applying the Doppler's effect to the model, wavelength of light doesn't match any space coordinate grid. There are 2 possible solutions. We can modify 2 coordinate grids, the one which is stationary for red sphere and the one which is stationary for blue sphere. But whichever one we'll choose, the initial effect will be exactly the same. Space coordinate grid will look like this. Now we have to decide to which sphere the new grid is supposed to be attached. Let's begin by making it stationary for the red one. And this is the effect. On first sight, everything seems to be okay, but after a second closer look, you might notice that there is one small inconsistency in the 30th frame of animation. Since in the simulation 1 unit of time equals to 10 frames of animation, at 30th frame, light emitted by blue sphere should pass full 3 units of space. However, according to the new coordinate grid, it passes around 3.3 units for the red sphere and around 2.3 units for the blue one. So, let's try now to make the grid stationary for the blue sphere. And it seems that now everything is working nicely. In 30th frame, light emitted from blue sphere seems to pass 2 space units for the source of light and 3 units for the red sphere, what is consistent with the rate of time-space expansion behind moving light source. Space gets 1.5 times longer right from the blue sphere, which moves at half c. Okay, cool. So everything seems to work nicely in the simulation. But now the question is, how can we use all of this to explain why light emitted in first frame will be observed by the incoming spheres in 20th frame of animation, and not in 17th one? The answer is in the fact that the modified coordinate grid can't be used as stationary frame, but has to be attached to the incoming object. If it would remain stationary, it would mean that distance in space observed by the source of light is being compressed in front and expanded behind incoming object for the stationary receiver. But the modified grid is moving together with the light source, what means that it's the distance observed by stationary receiver which gets compressed and extended for the stationary source of light. If you think that there is no difference, then let me explain it with the simulation. If the modified grid would be stationary for the red sphere, it would mean that distance passed by light in 13 frames, as observed by the blue stationary light source, is objective, and in the stationary perspective of red sphere, this distance is extended to 2 space units. This would mean that pulse actually reaches the red sphere in 13 frames of animation. But since modified grid moves together with the light source, it's the distance observed by stationary red sphere which is the objective one. And this distance is being compressed or extended in the perspective of stationary blue source. This means that light pulse emitted in the first frame of animation will reach the incoming red sphere in 2 units of time. All of this has some serious implications as for the perception of distance. If light emitted by blue sphere would reach incoming receiver in 13 frames, from the stationary perspective of red sphere, distance to blue ball in the moment of light emission would have to be observed not as 2 space units but as 1.3 units. However, since we are dealing with opposite situation and light doesn't reach the receiver in 13th frame, from the perspective of stationary light source, distance to the incoming object has to appear as longer than 1.3 space units. Although my simulation is at this moment unable to correctly represent the perception of space, I can still use it to show you that the distance between spheres is indeed being extended due to relative motion. But to do it correctly, I need to introduce a new concept which can be called as space clock, what should explain its purpose. If not, then allow me to explain that such clock, in the difference to a time clock, measures the distance which is passed by a moving object. My scenario is based on velocities and distances measured by a stationary yellow sphere, and I will base my space clocks on those measurements. Since for the yellow sphere, both red and blue spheres move through 2 units of space in 8 units of time, their space clocks will complete 2 cycles in 80 frames of animation. Here's how it looks like from the stationary perspective of yellow sphere. However, from the stationary perspective of both moving spheres, incoming object is passing 4 units of space in 8 time units. If we will maintain the number of cycles in the incoming space clock, its wavelength will have to be adjusted to a different distance. Just like this. Let's now look at the simulation from the perspective of stationary red sphere. I leave one space clock synchronized with yellow sphere, just for comparison. As for red sphere, there is no past distance to measure. As you can see, for moving spheres, distance passed by incoming objects becomes twice as long as for the yellow sphere. For red sphere, distance which it is passing is being nullified, while for the blue object it gets 2 times longer. Of course, longer distance means higher velocity. Incoming object moves now 2 times faster. And now things become interesting, as velocity is directly connected with time in space. I will try to explain how it works, but I have to warn you, this subject is a true mind squeezer. Here's the thing, Velocity of blue sphere gets twice as high, but its space clock, which is synchronized with yellow sphere, still measures the same distance. This creates an inconsistency which has to be in some way nullified. Let's say it this way. Since object moves twice as fast but it passes the same distance, time for that object has to flow 2 times slower to give a logically valid result. From the perspective of stationary red sphere, blue ball should complete 4 cycles in animation, but it is slowed down 2 times and manages to complete only 2 cycles. To make things clear, let's use a second type of clock, the one which measures time instead of distance in space. This clock works exactly in the same way as previous one, but is synchronized with the definitive timeline. Since my timeline is 80 units long, time clock counts 8 cycles in 80 frames of animation. This frequency is distributed along the path of motion. If we synchronize the time clock with distances measured by the stationary yellow sphere, we will get the frequency of 4 time cycles in one space unit. Would make sense as for yellow sphere other spheres are moving at 0.25 c. However, from the perspective of stationary red sphere, distance passed by blue ball is twice as long, which results in a decrease of frequency to 2 times cycles in 1 unit of space. In shortcut, time appears to flow 2 times slower. But now we have another problem. In 40th frame of animation, all spheres cross the same point in space dimension, and all time clocks show the same count of cycles. How can it be if time for the incoming object flows 2 times slower? You could possibly say that for stationary red sphere, time for the incoming blue ball flows 2 times slower, but when measurements of time are being compared, it turns out that things measured by blue sphere are inconsistent with things perceived by stationary red sphere. But such explanation isn't for me enough. I expect that things which are being observed are consistent with things which are being measured. Clock can't measure time which is different than the one which is being observed. If for an incoming object time would seem to flow slower than for a stationary observer, then there couldn't be any moment in timeline when both clocks would show the same count of cycles. Is it possible to find a logical solution to such problem? Well, you might guess that since I'm not happy with previous explanation, I've had to find a better one. Maybe some of you figured it out as well. All you have to do is to combine the space and time clocks with the Doppler's effect. We know already that due to Doppler's effect, time and space of moving object is being extended behind and compressed in front of it. In the case of my scenario, for the stationary red sphere, time-space gets 2 times shorter in front of incoming blue ball. So let's add this all together. From the perspective of red stationary sphere, time flows 2 times slower for the blue sphere, which is incoming at half c. But due to Doppler's effect, time seems to flow 2 times faster in front of it. You don't need complicated math to learn that as the result, from the stationary perspective of red sphere, for the incoming blue sphere, time seems to flow at the same rate as in stationary frame of red ball. However, such solution is valid only until the moment when motion paths of all spheres intersect each other in a single point of space dimension. After that point, blue sphere starts to move away from the red one, and Doppler's effect causes opposite result. But I'll deal with this subject in my next movie, as in my opinion I've fried enough brain cells of my viewers for this lesson. However, I need to warn you, until now it was just a small warm-up. Don't expect that it will get any easier from now on. But to finish this chapter smoothly, I need to discuss one more thing. I want to show you how to apply my model of relativity to a time-space diagram to get a result which is consistent with the simulation. Of course, my solution is as always the most intuitive one from all. All we need to do is to attach the axis of light to a moving object using time-space coordinates of a stationary observer. This is what you should get in result. Now everything what has to be done is to see if the diagram is consistent with my simulation. And just as you might expect, everything seems to work just fine. Axis of light, which is attached to the blue sphere, crosses the space of stationary red sphere in second unit of time, what equals to 20 frames of animation. It can't get any better. Time for a final test. First, let's use the time-space diagram to see at which frame from the perspective of stationary yellow sphere pulses emitted by both moving sources seem to reach red and blue spheres. According to the diagram, pulses of light are reaching red and blue spheres in 16 frames of animation. Now let's see if such result is consistent with the simulation. Well, it looks that everything is working nicely. From the perspective of yellow sphere, pulses are reaching moving objects exactly in 16th frame of animation. In my next movie, I will discuss a specific situation in which, due to relative addition of velocities, incoming object seems to move faster than the constant speed of light. According to special relativity, such situation is not possible, so it will be a nice test of my model. In the background you can see a small preview of things which you can expect to see in the next lesson. For the end, I want to summarize quickly everything what I did in this movie. Generally, I created a simple and intuitive model which explains how to properly apply constant c to standard Galilean relativity. I based my model on a single value of constant c and on the primary laws of relative motion. I didn't need to make any assumptions or unproved statements. I didn't need to make any sophisticated calculations, as each operation which I made in the movie is fully consistent with basic math. Each of my conclusions was based on results predicted by simulation. I began with constant value of c and basic linear motion, from which I derived things like Doppler's effect, length contraction and expansion, or time dilation, which here should be rather called as time shift. I did everything to avoid any possible logical or mathematical inconsistencies, so models should be paradox-free. Everything what was presented in this movie will be used by me as a primary base for all other physical models which I want to discuss in the near future. This is why my goal was to create a set of the most primitive and simplistic rules which are being used in physics, and I believe that it's not possible to create anything what would be more simplistic, straightforward and intuitive than the model presented here. And this is exactly what I'm expecting from the primary base of theoretical physics. In my opinion, foundation of physics should be based on clarity and intuitiveness. The less complicated is the theory, the smaller are the chances of making a mistake. Of course, just like most of my previous movies about relativity, this model of constant c in relative motion is completely against Einstein's special relativity. Not only it makes a completely different approach to the relativity of light, but it also predicts couple totally opposite results. My model doesn't use the Lorentz transformation of coordinates, so it doesn't include effects which are typical for special relativity. Time dilation and length contraction expansion are here just apparent effects of relative motion and don't produce any definitive distortions. My model uses a completely different concept of time. Instead of multiple determined and linear yet relative timelines, time is here described as wave function with an objective order of events and definitive simultaneity. In the difference of special relativity, this model allows to describe the frame of a photon and use the constant c as reference to relative velocities of moving objects, without giving any illogical results. Each of my statements, which seems to disagree with generally accepted theories, can be tested and validated in a laboratory. Of course, I am absolutely aware that I will be treated as a complete ignorant by the majority of scientific society, while my model of relativity will be probably rejected and ridiculed without any discussion just because of the fact that it is against generally approved mainstream theories. There is just one small problem, which most of physicists are unaware of. I know something what allows me to stare straight in face of anyone who considers himself a scientist and treats me as a clueless and complete ignorant. It's a kind of knowledge which lets me laugh together with those who made jokes about my pseudo-scientific fantasy and magical New Age fairy tales. Do you wonder what knowledge could it be? If I tell you, it will likely cause only more jokes and insults towards my person. But I don't care about it anymore. Laugh until you can, as I know already who will be the one laughing in the end. I can take every insult and handle each negative opinion, as I know that all of them will go back one day to the source, with much greater force and much more painful impact. Like everything what I do, this knowledge is plain and simple. It's the knowledge that there is only one truth and one way which leads to it. It can take couple months, years, decades, or even centuries, and maybe I will be long gone when it will happen. But if we won't kill our own civilization, sooner or later physicists will come to the same conclusions as I did, as there is no other way to understand the universe. And when this will happen, it will completely destroy the materialistic way of thinking. The stronger is the rejection of truth today, the worse will be the pain when the curtain falls. Most won't be able to handle the truth, but anyone who can survive a contact with its flame becomes once and for all certain and learns how to recognize the truth on the first sight. Are you ready for such experience? But if you really want to stand against my claims or wish to disprove this pseudoscientific New Age pile of crap, I will give you a hint. Try to explain the scenario which I used in this movie with special relativity or any other mainstream theory. Good luck. And with this metaphysical accent, I will end today's lesson. Class dismissed.